Hey everyone, how are we doing? I see William here. Can we run through number 4? Bro, I am with you. That makes me feel better. Let's go. Let's do it. Let's hop in here. I'm getting the assignment up. Just grabbing a little bit of lunch there in the background. Let me delete all this from my assignment. Number 4 says, looking at the VIS for the non-polynomial regression. Let's go take a look at that. Here we go. So we've got here, look at the VIS for the non-polynomial multiple regression model. Choose one of the variables and find how much the standard error has been inflated. Find the threshold for high VIFs using your standard error from the notes. Do any of these variables go over the standard? What does it mean to go over the standard? Okay, let's take a look. What does VIF stand for? So we're going to be talking about VIFs here in a moment, and any multiple regression model will have VIFs. What the heck is a VIF? What is a variance? What is that? It's variance inflation factor. Variance is actually pretty much standard error squared inflation factor. So when you think about variance, it's a measure of kind of lack of understanding or uncertainty in a variable. And you can see here standard errors in a model we have down below, which we do not want to inflate the standard errors. That'll make our intervals wider, make our p-values bigger. It's not a good thing to inflate your standard error. So when you're going right here, we're going to use one of our classic models for the moment. We're looking at the non-polynomial model. Wouldn't be in the rule if you use the polynomial. I'm going to use a model you should not be using. Don't use these models I'm using. This is a really crazy model right here. I'm just making it so we can look at some VIFs. And you'll notice right here that the VIFs are going to be for all the variables. We have lots of variables in this model. Please do not make these exact models I'm using. Try to limit your output to 3. I don't want anyone making this exact model I'm making. It's a little bit crazy. You're only meant to use 3 variables just to keep things nice and simpler. So once again, you're using your same model from last time or a model with 3 variables to keep your life a little bit easier with this right here. So when we look at the variance inflation factors, inflation of standard error estimate, we can go to a specific variable right here and see how much the uncertainty has been increased. This is using the generalized variance inflation factor. Should be all right. I did save it as M. Right here, we see desired weight. I'm not loving any of these. Let me do the following. Once again, don't use my exact model. I'm going to use one very similar to what I used in class. And I can just put the interaction. Let me use this model. Okay, now the output looks more similar to what you're getting. And so when you look at this right here, this is an interaction term right here. Let's take a look at it. The interaction term has with it a certain amount of what? When you talk about the coefficient right here, which we should always know how to get the t-value, this value right here represents our what? There we go, praise right there, the uncertainty in the estimate of the coefficient. And there's the t-ratio, and the bigger the t, the smaller the p-value. That's the way it's being calculated, by greater than a probability of the absolute value of t. So with this right here, I want you to think about this. Is there a magic number you know that's very close to 50, like 49? And if you think of VIF is equal to standard error squared inflation, then what does it mean that the VIF here is 50? In interpretation terms, the VIF of 50, how do we turn that back away from variance to standard error? Because talking about it like a variance, that's in squared units. So you want to do, if you think about it, I'll write it here in the chat, and we'll be seeing it. That's kind of how you can undo it. Square root, exactly. William, you're on the right track right there. You can square root it, and just think, since it's 50, and these are the numbers I like to put on the test, I'd probably put a plus or minus of 0.1 on this, so you could basically do it in your head. Because what does this mean? That we've probably increased our uncertainty, which is saying our uncertainty in this right here, like the amount of uncertainty we have, is probably about this much bigger. Our amount of uncertainty, because that's our uncertainty, it's probably about this many times larger. And if I were to put this on the test, I'd put a plus or minus of 0.1 on it. Of course, if you're solving it, you can just directly solve for it. But, this would help if people maybe have calculator issues, don't carry all the decimals. But all we're doing is square rooting this right here, which is the variance inflation factor. And then we can see that our uncertainty, because it's very close to 49, is going to be a little bit more than 7. And the plus or minus 0.1 would do it. So the uncertainty we have is about 7 times more due to what? And this kind of answers the other questions. So that's how we find this right here. That's how we find out what our amount of extra uncertainty, and this is our amount of uncertainty. It's probably about 7 times bigger, and that's what we have right there. Now, the other question is, what is the high threshold for VIFs? For that, we actually use the VIF formula, but do a model-dependent version. Who knows the formula for VIFs? What is the calculation for VIF? Does anyone know it? The calculation for VIFs. No, you wouldn't divide it by anything. You just take the square root of it. Yep. And that is how much uncertainty we have. So your uncertainty is about this much bigger, and then you wouldn't divide or anything. Oh, which question do you have, William? Let me know. You'll square root the VIF to find out about how much more uncertainty we have. So our measure of uncertainty is about, and then you just square root, like estimating, or our uncertainty in the estimate of the interaction term is about 7 times larger. So I took the variance inflation factor. Remember, variance inflation factor is standard error squared, so I'm square rooting it. So square root of VIF is the uncertainty of, not of the inflation, it's how much our, so when you think about what standard error inflation means, so we're talking about how much this standard error has been about inflated. So it's not the uncertainty of the inflation, it's the uncertainty in the standard error has been inflated by this amount. Does that make sense, William? That the uncertainty in the standard error, which is the uncertainty, is probably about 7 times bigger. Our standard error is probably about 7 times bigger due to the overlap. Kind of gets to a later question. Due to the overlap between the x's. They're all bringing similar stuff to this party, and that makes us more confused. So we have about 7 times more of the uncertainty. Like, our uncertainty is 7 times larger than what it would be if the x's were completely independent of each other. With only non-poly models, can we do this to any 3 variables? Yep. Just don't be using any models I use during my examples. I try to go outside the bounds because you can do this for a interaction term, which we were doing today. So I try to go outside the bounds of what we should be doing and like what I would expect people to do on the assignment. So I would people to do exactly what I do. And the formula for VIF is 1 over 1 minus r squared sub I. And that r squared sub I for number 2, once we get our poly model, is that all we do? What exactly we do? We look at it and talk about when we compare. Let's look at it. I think compare the r squared. I think that's just it. As long as I would just print out the summary of the model. Aisha, good question. We can talk about that next. I'd print out the summary of the model, get your r squareds adjusted, compare them, just maybe comment on it. But as long as you're meeting the standard, just make sure you can show it. Make sure to show your work. Like, don't just be like, I found the r squared adjusted and it's this. Be like, show it in the output. So a few people have lost points for like not showing output, like because I can't check your work. I don't know where the numbers come from if I don't see it. So right here you see the formula for VIF. What is an r squared sub I? Pretty important for the test. What is an r squared sub I? What the heck is an r squared sub I? R squared sub I? R squared is the percent of variation in y explained by the variation in x. What is r squared sub I? It's for the ith what. And we'll have one of these for each of these. R squared sub I is not a good thing. Kind of the x's. It's the way the x's. It'd be the ith x explained by all the other x's in your model. So you'd take all your other x's and you'd build a model explaining x from your other x's. So the ith x is explained. So every single x is explained. Like you would look at how your first x explains the other x's. And this is not a good thing because look at the way the formula works. When r squared sub I goes up, everything gets hurt. So r squared sub I going up will make variance inflation factor worse. It'll make us more uncertain. So this is a measure of basically the multicollinearity because we're looking at the way in which the x's explain the other x's. So over here you have your x's explaining one of your x's, the x sub I, which it can be done for all of them. Does that make sense there, Trace? Like, The r squared sub I is how the ith x, which can be any x, the first, the second, the third, the fourth, is explained by all the other x's in the model. Y does not come into play right here with r squared sub I. So the sub I represents the ith x, and it's not a good thing. You do not want a high r squared sub I because that would indicate multicollinearity. That would indicate that the information in this x, whichever x we're talking about, is contained in the other x's. So it's bringing, well, what kind of information is it bringing if you have a high r squared sub I? And this is the good conceptual stuff to know. If you have a high r squared sub I, that indicates this x has what kind of information with it, which then it's not bringing new information, which is what we want it to bring. Redundant, Michaela, great job right there. Let's throw out some points. We haven't thrown out some points. Mubot should still be awake. We don't, r squared sub I being high indicates redundant information being brought to the model. And then this can be measured via the variance inflation factor, which is going to tell us the extra amount of uncertainty we have, which is also another name for multicollinearity. Like the uncertainty here is multicollinearity coming into play. So with this, how does this relate to the assignment especially? We use this equation to create a model-dependent standard. And all we do is do this. Now, this is the standard. We're going to take our model's r squared, and to see, like, well, we have this much variation in y explained. Well, then dependent, our model-dependent standard, is literally just taking this and doing 1 over 1 minus. And our model-dependent standard is 2.7. Are these high? Yeah, they are. And probably because they're interaction terms. So the model-dependent standard points to we do have a high degree of multicollinearity in our model right here, which is not a good thing. That means there's too much overlap between the x's. Doesn't invalidate the model. It's just something we don't like. Don't like it. Not good. Not the end of the world. And so that should do that right there. That's the threshold for the high VAF. Do any of your variables go over this standard? Yeah. Yes, yes, yes. All variables go over this standard with values that are much greater than the value of 2.7, which is our model-dependent standard, i.e. being 50, 14, 20, they're all way above. This means that there's a lot of redundant information being brought to the model by the variables we are using. This does not invalidate the model, but it's not a good thing. Maybe we could look into this. That's got that one. Let's hop back. What additional questions are there? Throw those questions out. Just found out someone in my department is leaving. No, they got a good job though. No, it's other schools trying to take our best teachers. That's okay. I'll miss them. It's a bummer. Got a lot of great people in our department. And so I was literally thinking a week or two ago, I was like, we haven't had anyone leave the department in a long time. Like 7 years or something. And do we compare the poly model to the complex ones for r squareds adjusted? Number 2. We'll take a look at number 2. Let's go to number 2. Compute r squareds adjusted. Compare. Yeah, make sure to write a comparison right here. So let's go look at number 2. For number 5, do you just compare the r squared adjusted? So look at number 5 next. Let's take a look at number 2. Here we go. So with this one right here, we can show how to make these again, but check out yesterday's video. We'll keep taking questions. I'm going to speed run some questions here, but then if you're like, hey, how do you make that poly model? We can go back and look at that. So we're checking for nonlinear relationships using the choose order. Now you have to create your simple models here, and you have to run the choose order on it. So make sure to review how to run the choose order, and that's going to tell you the order by which you're creating your poly model. And we show here the poly function. Went through it yesterday twice, but feel free to ask. So when you get this poly model right here, you'll have an r squared adjusted. And the goal of this, which it's hard to get down here to the compare r squareds adjusted, because you really want to look at this value. We'll put it right there. And you want to look at your r squared for your original model. R squared adjusted. Why are we using r squared adjusted? Well, r squared adjusteds are adjusted for how many variables are in the model. So you could maybe go here and put a table, store into the table the first, we don't want to do it in quotes, it wouldn't be that enrolled, and second value, and let's go here to names of the table, and the names of the table are going to be regular and poly, and then print table. There we go. Some of my variables VAFs go over the high threshold, then Not that, and here's a good Trace, great question. It wouldn't be that they are bringing with them new information. It would be if they are statistically significant, but the redundancy in your variables is not very high. So I might have misspoke earlier. Trace, I'm throwing you 20 points because maybe I misspoke. The goal is that they bring new information, but having low VIFs, you could have a variable with a low VIF that is not bringing with it new information, but it's just not bringing with it redundant information. So VIS would not tell us about new information. New information being brought by the variable would be the p-value. So it's possible for something to bring a bunch of redundant information and be statistically significant. It's also possible for something to not bring redundant information, i.e. low VIF, and maybe like this right here, because I bet you this does not have a high VIF. And so you see right here, GPA has a very low VIF, but GPA is not bringing with it new information. It's not bringing redundant information either. It's just showing up with nothing we want. So it doesn't have new information. It does not have redundant information. Desired weight, looks like we have about 2 times the uncertainty, and a lot of the overlap is probably between desired weight and weight. And so VIF under the threshold tells us that there is low redundancy. Yeah, redundancy, and these have a decent amount of redundancy, higher than I would like. The lower the VIF, the less the redundancy, and so it means they bring little to no redundant information. Yeah, this is not redundant at all with the other X's. I could actually calculate this VIF, and then we got Michaela's question next. If I wanted to calculate this VIF, I would go right here. I think I can store this into this. I don't usually use the formula format this way, so I'm going to try it, though. If we go here to GPA, and we put in GPA, will that work? Yep, it works. I just don't call it formula when I do it. What about collinearity? Collinearity is just between one X and another X, and we usually focus in on multicollinearity. I guess you could go into subsets of collinearity. Be a really good question right there, William. But usually we just focus in on the multicollinearity, which this is now a multicollinearity issue because it's how is GPA explained by these two. And you can actually see it right here. GPA is the Y variable, and the X's are now this. So I'm actually going to compute this number here, this 1.05, by doing a summary of this model where we're predicting GPA. And look at what I do. I take the R squared, and I go 1 over 1 minus R squared. And look at that. That number right there, that 1.05, pretty almost decimal place accurate. It might just carry out more decimals than I do. But does that make sense how I calculated this? The way I calculated the R squared sub I, we kind of jump back to this and we got Michaela's question next. The way I calculated this R squared sub I was I actually had to make a model predicting GPA from the other X's, which goes to our theory for this, that the VIF, I drew it on another spot, the VIF, oh no, I had it. There we go. The VIF is when you take one of your X's and it goes in the position of Y, and then the other X's become the predictors. So that's what you're seeing right here, where you see GPA, which was an X in the previous model, becomes the Y variable, and then the other X's become the predictors to explain the variation in GPA. And this has a rather low R squared. We run it through the equation 1 over 1 minus R squared sub I, which you see right there. And that tells us the variance inflation factor, which is about 1.05, which means GPA really doesn't have much. Think about it. I mean, when you look at this R squared, has a rather small overlap in the variation it brings. Only about 5%, a little less than 5% of the variation in GPA is explained by the other X's in the model, which are desired weight and weight. GPA looks to be unique, I'm not saying good or bad, unique in the information it brings. And we see this especially through the variance inflation factor. And that was calculated for us. So we don't have to make all those models and do it. It'll do it for us. And then you got it. You bet. You bet. And then GPA right here just doesn't bring new information that would make it stand out. It doesn't bring redundant information either. It's just kind of a bad variable. Let's hop back to space and then do Michaela's question. Music, music, music. I like this one. Always like this one, Shell. Okay, here we go. Michaela says, for number 5, do you compare the adjusted R squared values between our models? Let's go take a look. Number 5. Here we go. Create a variable. Ooh, I think that's what Trace was asking. So we'll combine questions right here. Create a variable from 2 of your 3 variables and add it to your model. Does this variable bring new information? How do you know this? Yep. Worrying about number 5. Let's do it. So how do we create variables? Which, in technicality, now don't use mine. I've done it right here. This, oh no, we don't got the interaction anymore. Let's go grab an interaction. The creation of a variable mean, yeah, technically, you know, don't do interaction. More traditionally, a creation of a variable is going to be when you, it's basically like a transformation, but you can create it from subsets of your own variables. You can use ratios. You can add two variables together, divide by another variable. You can do anything you want. Let's create the craziest variable we can think of. Let's just go right here. So we have our model that we've been working with. Don't use my model. There's a model we've been working with originally. Should be just stored up there in a common place. I'm just showing you so you can see that height is being explained by weight, desired weight, and GPA. I'm going to go right here and I'm going to call this new variable. And we don't usually capitalize unless it's a data frame. New variable, I'm going to store into new variable the following. I'm going to go to survey 10. I'm just going to start grab bagging stuff. I'm going to go here to someone's GPA. That's a horrible variable. It's in the model anyways. I'm going to go here to someone's desired weight. You say, Brian, that's in the model. Well, too bad. I'm going to go and divide it by somebody's weight. So I can see if somebody desires to weigh more than they weigh. So when you think about this variable right here, a positive number means I want to weigh more than I weigh. A number of 1 means I weigh exactly what I want to weigh. A number of 0.88 means I desire to weigh less. Because think about this. You'd have to do something like, I want to weigh, 166 pounds, and I currently weigh 200. This would create a number less than 1, and you can see it right here. So that's 0.83, which is someone like in this range-ish. Those are kind of close. There's a person who's a little closer. So we just want to understand how this works and what we're creating. We're creating a ratio of what someone desires to weigh over what they weigh. Well, let's go another bit further right here. Let's also... I'm trying to think of another variable that just would make sense. I know the data set's pretty well, but... So we're dividing that ratio. Why don't we add to it how many video game hours you play? Let's add to this how many video game hours you play. And yeah, why create this? I don't know. Can't really justify the last part. Now, I did this kind of in a step-by-step process. I created my new variable, but now what do I need to do to my new variable? Who knows? Help me out here. What should Brian do to his new variable? I need to take my new variable and put it where? Where am I going to put my new variable? Because if I'm going to write my model in this format, which I often like to do, it's going to need to go somewhere. That variable has to go somewhere. In the model, yes. Stored in the data frame right there. Yep. Now, you could do it. There's many different ways. You could just go right here and do that. It's getting really long. Perfectly fine to do this. Works. Don't worry. Works. It's a graphical error because of the plot over there. That works. If you don't want to do it in that step, you could go here and call new variable, which yours won't exist. So let's pretend we didn't do that. Survey 10, $, new variable. There we go. It's gone. So now when you're doing this, you will see new variable, and you won't see it because it does not exist right now. I deleted it. When you null something out, it goes away. And now you just put a new variable right here. So now when I create this, it will create that space. Don't go through here and null it out. I did that so that you could see what you would actually see. The reason when I'm typing it now and it starts auto-completing on new variable is because it exists. So I removed it to show you can store to things that don't exist, like anything you want is possible. There we go. And now if you go here and you type whoa, what? That exists? Sure. Just store it to wherever you want. But when you first type it in and you're just like typing random things, it won't exist. It should double check. Make sure the vector exists. One way to do this is to highlight the vector you've already created. Make sure the vector exists. And then just store into new spot. And then when you go here and you check out new spot will have the information in it. So make sure the vector you are writing right here by double clicking it will highlight the code. Make sure that exists. As in, I am not looking at this over here. I'm looking at this right here. Nice job, Trace. Thank you right there. Just sometimes you maybe didn't run the code or something happens. It literally, has anyone here had a mistake that literally you just ran the code and it fixed itself and you're like, well, I was working on that for 10, 15, 20 minutes and I just reran the code and it worked. There should be me just now. There should be a compilation of Brian going like this whenever his code works and he just doesn't understand why. And you could probably trace it back to like, I didn't run a certain line of code, or I had an error, I'm missing a comma. Sometimes I run code and my R doesn't actually run it. Oh no, no. It's always like looking at like where these little errors coming from are. Little bits of errors. So we got right here the new variable. There we go. We don't actually need this model. It's just for show. And I wouldn't print this out right here. Watch out. Be very careful. Look at your assignment after it knits. A few people have gotten dinged for excessive output. A good way to immediately crash and fail your assignment is to do something like that. That little of code, big problem. So our new model has a higher square adjusted. We wouldn't say that would... So if this variable is bringing with it new information, where is that going to be contained? If this variable is bringing with it new information not contained in the other variables, watch it be like watch this get like an R squared of 1 or something ridiculous. If this variable is bringing with it new information, where is that going to be contained? The answer is, wow, whatever, sure. Did not expect that. The answer to whether or not this variable brings with it new information, which the answer is yes. I just solved the world. I did it. Where do we know if this variable brings with it new information? P-value of the variable. How does it just does. This p-value right here, it denotes that with the other variables that are already in the model, then this variable brings with it new information not accounted for by the other ones. It might have an overlap. You don't have to look at that, but I mean, it goes back to reviewing it. What? This variable is very not redundant in the information it brings, and so you can see the similarities. Where this one is not redundant, does not bring with it enough new information to be statistically significant. This one is also almost as the same, not redundant, but brings with it amazing new information. This is where you're at a party and there's pizza, there's cookies, there's Coke, there's Sprite, and then someone walks in, they said, I brought Swedish fish. How you feel when that person says, they walk in and they say, I brought Swedish fish? Is anything I mentioned, maybe cookies a little bit, like this is that little tiny bit of cookies overlapping right here because they're sweet. But that person walks in and said, I brought Swedish fish to this party. And you're like, bye-bye diet. I was trying to be good. It's Friday, it's my cheat day. It's the weekend, it's my cheat weekend. It's my cheat week. It's my cheat month. What do you say about that person bringing Swedish fish to the party? What they brought was very unique. So you look at the p-value, see if the new fish brought. Yep. The adjusted R squared is going to tell us an even comparison of models. For any models that are trying to predict height, the R squared adjusted is going to compare models on an even playing field. So the I think I have always said in class that if variables are bringing with them new information, like if you just, some people will look at this, they'll look at their R squared adjusted as they add in more variables. That's one thing you can do is like add a variable, look at R squared adjusted, add a variable, look at R squared adjusted. You can do that because if your R squared adjusted starts going down, these variables are probably not a good idea. But you're also going to see it show up right here specifically because probably, tell you the truth, if I just go right here pretty quickly and just remove GPA out of this model, GPA was not bringing with it new information. Remember this number right here. We'll copy it so we don't forget it. And so you can see, there's the previous number. What happened to R squared adjusted when I removed out GPA? Yeah, we can go back and talk about that, Aisha, if you want. I think we have, but we can go back and talk about it. What happened? So if I have a p-value of 0.6424 for my new variable, it does not bring with it enough new information to be statistically to make it exactly traced. Yep. And look at what happened when I removed GPA right here. What happened to R squared adjusted? When I removed GPA, R squared adjusted did what? I mean, not by much, but it's something. And did R squared go down? R squared did go down. So R squared went down, whatever. But R squared adjusted went up. So because GPA is not bringing with it enough new information. Does that make sense, Michaela? So you could look at that, but specifically the p-value right here denotes whether or not it's bringing with it enough new information to be statistically significant, and it's probably up for removal. There's a lot of different techniques to figure out what variables to remove from your model. Like variable selection is a big important thing. Awesome. We can do that next here, Aisha. You got it. And I think, how's everyone doing on these? I think we've answered a lot of questions related to them. Let's see right here. Awesome. Great job, Michaela. Great job, Aisha. Great job, Trace and Brandon. Everyone, good to see you. Let's write some points right here. Do I still have the points? Yeah, I don't have points. I'm done. Thank you. You're welcome, William. Excellent work. Let's go look at sum number 3. Can you go over an interpretation of an influence plot real quick? You bet. After this one, we're going to do number 3, and then interpretation of influence plots. You got it. Let's do it. Just try a little music right here. Just chill. Go get that second cup of coffee here in a little bit. Woo! Second cup of coffee. Number 3. Number 3. What's number 3? Create a simple model with one variable and compare it to your model using a partial f-test. Okay, so we already got a model. So we'll start from scratch. Let's go look at number 3. So the point of a partial f-test is to compare two models. We've got it in here somewhere. Oh, there's our partial f. Where'd you go, partial f? There's the partial f. So when you look at an f-test goes from the naive to the full model. When you look at a partial f-test, especially for us, it'd go from a simple model to a complex model. Complex models just have more variables in it, and our goal right here is to reduce the sums of squared error. So the reduction in sums of squared error is basically just error. Why is it sum of squared error? Error is just a residual. It's how much we miss by. We will square it so they're all positive because we don't want them to be positive and negative because we are going to sum them. So we are going to square them, once again, all positive, and then sum them to get a total amount of error. So our goal is that we have less error when we get to the bigger model. So the p-value down here, whichever test we're doing, a full f-test or a partial f-test, is going to tell us if this error actually gets smaller and the reduction is unlikely by random chance, i.e. low p-value. So when we go here, we need a simple model. Well, once again, don't use my examples. I'm going to call this model x1 because in my, yours won't pop up. I've already saved these once. What we have right here is a linear model describing height, because that's the one I always use, predicting it from weight. That's y tilde x, comma, data equals. Make sure to use this format because some of the codes take this format. We can look right here at the model. You don't need to, so probably don't include this code, but here's our model. 36% of the variation in height is explained by weight and all this other good stuff here. So we need our original model, which I have my original model up here, just called M. A lot of times people will call this a complex model, so for the moment I'm just going to call it complex. Sometimes people might also call this simple. Now, it doesn't have to be a simple linear regression. It can be a multiple regression. It's just a simpler model than the complex. This model has one variable. This model has 3 variables. And you can see the variable differences in here. I'm showing it for a specific way. If you look at the partial f-test. It doesn't have to go in the same order, but I think it helps to see this. That when you compare the simple versus the complex, and usually put them in this order. I have too many complex models to, capital simple. There we go. The amount of variables different in the model are how many? How many variables are different between this model? How many extra coefficients, I should say? At this point, we haven't done any indicator variables. But how many extra coefficients does the complex model have compared to the simple? How many extra coefficients does the complex model have to the simple? And you can see the coefficients. Great job, Trace. Rep 2. And that's coming from a coefficient for desired weight, a coefficient for GPA. And you can see it down here. That's why I put them in order, because they both have weight inside of them. So what am I talking about? Coefficients. Aisha, great job. It's the capital simple. You can see here the coefficient of weight, 1 coefficient. And you can see right here in the complex model, 3 coefficients, 2 coefficients here. And what's interesting is weight, gets less significant, probably due to multicollinearity we've been pointing out throughout today. And so, yeah, when we're in the partial F, what's the output say? Well, this is one of the things I slightly care about. It's the difference in the coefficients in the model, denoted right here. The extra variables make extra coefficients, just depending on types of variables too. The F statistic denotes how much more variation we are observing be explained than by random chance, or what we would expect by random chance. And the p-value right here tells us the reduction is statistically significant. Remember, we're talking about the reduction in the sums of squared error. And so it's very important to know that we're saying, is the reduction statistically significant? So is the reduction, how did I lose that? Oh, there it is. Is the reduction going from the one variable model? And in this instance, we're going to a 3 variable model. We have 2 additional variables. So is the reduction statistically significant? So what's the point of a partial F-test? To compare two what's? Which I guess an F-test does that too, but it's always the naive. So what's the point of this? And this is always the naive down here. What is the point of a partial F-test? So when you think about an F-test, it's always to compare a naive to our model to see if the reduction going from here to here is statistically significant. But then the partial F-test, I'll put so I can see the full screen. Yep, simple to complex, and basically just 2 models. Big model, small model. The question is, should we add in these extra variables? P-value here would say no, but ours comes back P-value of yes. So you're saying do these to see if it could be a polynomial model, just a bigger model. Good question. Good. I'm glad I asked that question, Trace. 20 points, Aisha and Trace. It's just comparing 2 models. You say, which of these models is better, the bigger or the smaller one? Well, let's see if the bigger one brings with it new information. And the answer right there is yes. The bigger model does bring with it new information, and the amount of information it brings is unlikely by random chance. Like the reduction in sums of squared error that it does is unlikely by random chance, i.e. it brings with it new information that we don't think is probably due to random chance. Is that making sense right here? You're like, okay, new information is brought. We got it. Let's head back. We're going to do some influence plots. Influence plot times. Everyone was hating on some influence plot yesterdays. We'll go over here to this one. Everyone was like, man, I hate me some influence plots. Awesome. Great job, Aisha. Excellent work. Let's look at some influence plots. Let's go look at one. Here we go. Look at the influence plot and mention if any of the points are high influence points in the model. Talk a bit about the extreme nature of the points and why they are influential in the model. Okay, so you need 2 things to be influential in a model. What 2 things do you need to start? What is one thing you need to be influential? Like this point down here, not so influential. I'll move it further away. I'll move it way over here. Not influential. Send it to me, William, and I should check about that. Send me an email and send it to me. I'll check that right after, if we have a lull between this. What up? Getting ready for Time Series. Ben, so good to see you. I'm excited. Ooh, got a lot of stuff. Ooh, getting Time Series ready. So we see right here, there is leverage. So this has leverage, but it's missing another component. It's a more complicated than we make it sound. The other component is the following. Right at the top. Deleted studentized, not a word, residual. Come on, word. Get mad at me. Tell me that's not a word. Is it a word now? Have we changed how words work? Okay. So the deleted studentized residual, what the heck is that? Well, we all know what a residual is, or most of us, that's all right. And we might have points like this. Boop, 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 boop. And then we got this point down here. Now, if we let this point have its way, it's going to take that line and pull it down. So this right here is E, which is the residual. But if we delete that point, then our line would look like this. And this is the deleted one portion of it right here. This is what it means to delete it. So when we delete it, we're just removing its influence and calculating a line without it. But now look what happens to the residual when you delete it. It goes E, like that. So now the deleted studentized residual is always going to be larger. And so that's just the residual component of it right here. So we see the residual is just how far we miss by. down there on that. And then what is the studentized? Well, when you see studentized, just think standardized. We're just being mean here because the only thing you should care about right here is the T portion of it. And we know T's are basically Z's. So what do I mean by that? Well, if you think of something that has a high Z-score outside of -2 or 2, same thing works for T-scores. So studentized means it's been standardized by the T statistic. So that way, if I tell you we saw a T-score of like 5, you'd be like, whoa, that's huge. And so I'd be like, how do you know that's huge? Well, it's studentized. If it's greater than 2, that's big. If it's smaller than -2, that's very small. Or outside the bounds, very low value, very high value. Not very small, I should say, an extreme value that was way lower than our model would have predicted for residuals. So we have right here, studentized is turning it into a T statistic, which is a standardized way to look at these. And that's what we're going to see here on this plot. I'll disappear so we can see the plot. Is we're going to see the leverage, which tells us how far away something is from the x's, the mean of the x's specifically. And we're also going to see, let's do the m.complex complex we were just using. Ooh, oh my gosh. Now, if I'm going to break this down right here, we got some stuff that this is, I got a paragraph one right here to talk about. Oh man, there's a few things in here. Okay. Overall total, we got this right here. You can actually find that out pretty quickly if you go back to your code, take this, and since I don't like, good, that's that. Let me take this, copy it, and go length of that. So there's 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't like counting things. If yours comes up with more than this, and also if it wraps the screen, it will tell you which position you're at. So you could see here, this is the 7th, the 8th, the 9th, the 10th. So maybe you get lucky and your screen looks something like this right here. And you're like, oh, wow, there's 10 total influential points. So with these 10 influential points, we can see here that we got this ridiculous point over here and some clusters down here. So what's going on right here? Well, a few things to point out. This point down here in the bottom, the size of the circle is the size of the influence, which is the Cook's distance, measure of influence. So the bigger the circle, the more influential the point is. And we've kind of got these ones down here. Overall, it looks like we have two groups of influential points. The most influential point, which I could narrow down which one that is at. If you want to find out which point that is, there is a way to do it, and I'll show you that way right now. That point has a leverage of 0.15, which is how far it is away from the mean of the x's in a standardized format. And you need to have library dplyr. Make sure you use install packages dplyr and do not include this in your knitting. Like, I'll show you what not to include. And then, nope, we just had a blink on the internet. Hopefully everyone caught what I was saying. Why you do that, internet? Oh, broom. I typed bloom? Now it should do it. Hey, there we go. So I think this should work now. What models are we using for any of them? Just to make sure you understand it. As long as try to find one that has something of issue. If it doesn't, I guess you could mention that. Maybe get lucky and it doesn't have any highly influential points which are causing undue influence on the model. I think the code now is Tibble of my model. And I was looking at the m.complex model. No, it's augment. I'm trying to learn new. There it is. There it is. So what I'm actually going to do is I'm going to call this data. And I'm going to go look at it. The reason I'm looking at it right now is it's pretty easy to identify. This is just an above and beyond portion. It's pretty easy to identify the high leverage point. That is known as the hats. And you can see right here, that is going to be row, it's this individual right here. We don't get the original row number. And it's more, I can get that if I want. Let me store that. And then let me go to data. Let me go to data, number, and go to row names, data. Okay, now, okay, good. Should have it now. Now, when I sort it by the hats, I can get the row number for it. It's row number 544. So I just took the row numbers and stored it here as a variable so I can tell which person it is. This person is person 544. We could now take a look at them by doing that. There they are. Well, we can look at them in the full data frame. This just has their X and Y variables. If we want to see more info on them to see if they answer our survey honestly, we were using survey 10. And this really is the person to focus in on. This person right here says they are a male who is 75 inches tall, who weighs 75 inches pound. Hey, what's up, Adam? Good to see you here, man. And I think they just made an entry mistake on their weight. I think they meant to put, that's another redo of their height. My hair's all short again now, Adam. So I think they just misentered something right there. I think that's the only error. But really, when it comes down to it, when you look at these plots, and this person right here with these extreme values, the model misses one more week of classes. I know, right? Craziness. This person right here has ridiculous leverage, which means that their combination of X's is extremely weird. The model also misses them by a good bit. Then we have like a subsection or another set of people who have, a lot of them have very low residuals or deleted studentized residuals, which means the model overpredicts a lot of them. They have decent amount of leverage. And this individual right here, the model underpredicts because the model is going to be here at 0 going across. And because that's something with a deleted studentized residual of 0 would have be on the model. And so is this making sense? Does this help here, Michaela, to talk about what's going on? These are people. This person is extremely weird in their combination of X's. Like, I think it's because they want to weigh 250, I think it is. They want to weigh 250 pounds and they weigh 75 pounds. So these are their X's right here. And that's what's creating this super weirdness on like, wait, you weigh 75 pounds and you want to weigh 250? What? And that's what's creating this weirdness on the X scale. So the weirdness on the X scale means your combination of X's. I had a point in the bottom right too. Yeah, that means your combination of X's, depending on how far over it is, this means weirdness in the X's right here. Like the weirder you are in the X's, the further you go over here. These are the people who are near the regular just mean of X. Like we'd find something, this is called the Hatz matrix. The most common individuals we see, this person weighs 152 and wants to weigh 145. This person weighs 150 and wants to weigh 145. This person weighs 153 and wants to weigh 150. And just think about that. Like if you talk to a random college student and they say, I weigh 160 pounds, but I want to weigh 165. You'd be like, yeah, you sound like a typical person. And then you talk to someone, they say, I weigh 260 pounds, but I want to weigh 150. And you're like, that's a lot of a change. This person says, I want to weigh 95, or I am 95, I want to weigh 95. They got their goals. They have no GPA, though. GPA 0. This person says, oh, you see, that's probably where they're odd right there. That's probably where the oddness is coming from. You're like, you have a GPA of 0? So will the residual of your points be large since the mean cuts off at 0? Trace, can you expand? I think I might need to elaborate on that. So the residuals are only looked at in terms of this distance right here. So these lines right here are the residuals. Residual has nothing to do with this leverage right here. That's nothing to do with it. It's only this distance right here, which would be the up-down distance. So this is, in terms right here, small. And this would be large. Only residual. Which this would be for like all those areas. Yeah. So deleted studentized residual is only the up-down different distance, and then leverage is the left-right distance. So like a point over here is not influential. Like if there was a point that exists over there, that point would not be influential Y. This point right here is not influential Y. It's got crazy leverage. It's got even higher leverage than the other one. And it probably looks something like that, like a little dot. It would not be influential or not very influential. We could look at this Cook's distance. Darn statistics and all their calculations. Graphics are better. Why would that point right there, that green point, not be influential on the model? If you looked at it, if this was the simple world, that green point would probably look something like this. Meanwhile, that red point down there would look something like this. Actually, it's got to be a little tiny further back. So you can see here's the red point down here, and there's the green point. And kind of on the mean. I wouldn't really call it the mean. Well, yeah, I mean, the line's the mean. The line is the mean of what we predict y value to be, but it's on the line. To be specific, I can show you, it might help to see it this way. I think it can help when I make the influence plot look this way. There we go. AB line, horizontal equals 0. Line width. There you go. So that's the line right here. And i.e. this point right here is well below the line itself. So if you're looking at a model, I don't know if I have a simple model in the picture right now. It doesn't like that because that's not a simple model. If you have a model right here, here's your line, and this is a different model, but there's the line. Oh, we could just do the influence plot on it. So let's go right here. Let's take our influence plot, and let's just do it on the simple. So what you're going to see right here, do you see this 3-point structure, that 1, 2, 3? That 1, 2, 3 should be visible, and there's the 1, 2, 3. The 1, 2, 3 is right there. You've got a point at the upper end of the model that's basically on the model towards the high end, and that's that point right there, just a tiny bit below the model. And once again, we can view that right here. That point's a tiny bit below. Got another point a bit below at the far end of the model. But I think what maybe confuses people a lot of times is this point right here. Where's this point at? This point's actually going to have decent leverage, and that point is actually right here. Because leverage of 0, this is where people usually get confused. Leverage of 0 actually means you're in this area. Why is a leverage of 0 in this area right here? And I'll answer the question with using this. Why is a leverage of 0 in this area right here? Like on the previous graphic, when it says a leverage of 0, why is it right about here? And actually, we could add that to it. Yep, mean of the axis, yep. So what you're literally doing is you're taking this and folding it over on top of itself. Like you're taking this graphic, and it's so hard being mirror image, and you're folding that portion on top of it. You're like you're taking like, I wish I had a sheet of paper, and you're just folding it like this on top of each other so that you would take and just do this. Does that make sense? Like, does it be this hand? Yeah, there we go. All right, here we go. You're taking this right here and just folding that portion over like this. Does that make sense? So 0 is going to start right here on this next graphic. It's going to, once again, you're taking this graphic and folding it over like this. So that's why this point's going to come this way over here. And when you look at it, you're seeing, there we go. You're seeing this right here. And I'll put the purple line on here too. Give me a half second. Where'd my purple line go? So that purple line you are seeing. Oh, is it right off the scale? We can't see it because it's so close. I don't like that. There, okay, that's fine enough. Okay, good. It's 0's not showing, so you can't. It's right around there. So what you're seeing, let me show them both. Maybe it'll help to see this. Is you're taking and folding this over on top of each other. Most of my points stretch vertical, likewise from -2 to 6. Then you've got some extreme high points right there. There's some extreme high deleted studentized residuals. And then one in the bottom right. Then there is an extreme leverage point. Yeah, that might not have too big of a deleted studentized residual. If it only goes to -2, then you see mine has, this new one right here has 2 extreme influential points that have slightly high leverage. If you look in turn, I mean, they're high leveraged by denoted here. This is where high leverage begins. They have moderately high leverage along with some less influential points, but they have a very high deleted studentized residual as denoted by -6. And this one right here is less influential, has a little bit less leverage than those two, but also has a slightly high deleted studentized residual. These have higher deleted studentized residuals, more negative. There's another point in here. I think there's 4 points total on this. You can see the 4-point row numbers right there. But does it make sense how I'm showing how you're taking this graphic and folding over here? That's why this point's going to go this way, and you see it right here. That point right here is this point right here. So Good stuff. Is this making a lot more sense? Awesome. Yeah, a lot of people yesterday were wondering about this one. We really went in depth, and hopefully graphing this out, adding a few just lines to it makes more sense. Like the red line in this graphic right now, this red line right here is the line I added to the graphic right here, the red line. It's still the same red line. This purple line right here is where we're folding this over on top of itself. So you see these 3 points over here are actually what's going to come over here, and we see those, I guess right in here, I think those might be the 3 points. These are the really low 3 points, like down here. But these 3 points that have this pattern, they don't really have that high of... They might be right here. Those might... It's hard to tell exactly where things are at. It's easy to identify things like that. That little tiny speck right there. That little itty bitty... Is it smaller? There it is. That little dot. See, little dot, 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 all three below the line. You go and you take a look. Little dot right there. 1, 2, 3. Those are those 3 dots that are right over here. 1, 2, 3. And look, this one should have a little further distance. Maybe leverage grows in a way that I don't... Yeah, I need to look at a leverage equation. But 1, 2, 3 right there. And then you go back here and you go 1, 2, 3. Good stuff. Good stuff. It's graphical illusions. Let's head back here to space. Well, got a lot of the assignment done today. Went over a lot of parts. Are people done with the assignment? How are people feeling about that assignment? How do people feel about the assignment? Feeling pretty good. Assignment. Good stuff. I think a lot of people are done now. I'll take a look at some emails here. But keep working hard. Keep asking those questions when you're stuck. Just let me know. Just be like, hey, Brian, assignment's not working. Can't get this code to run. Doesn't make sense. What are we doing here? What's a polynomial model? How do I make those polynomial coefficients? Next time we'll really start tonight. Awesome, Michaela, great job. Feeling better now, about to submit. Awesome. Well, keep up the great work. Keep asking questions. Let me know whenever you're stuck. 1 week, we'll be done. What do you think about that Puppet Shark? I'm not Puppet Shark. You're welcome, Michaela. Bye for now, everyone. Bye.